Hi, welcome to week 2, part 2 of Soil 360 at Humboldt State University. And what we'll do in this video, which will last about 20 minutes, is we will talk about subsurface diagnostic horizons and other diagnostic characteristics. And before we start that, we will talk a little bit more about epipetons and mollic epipetons in particular. So what I'd like you to do is please have your keys to soil taxonomy ready in front of you if possible. We're going to be working with chapter 3, especially on around page 11 in the 12th edition of Keys to Soil Taxonomy. What I'd like to introduce here is a classification checklist, and this is a handy organizational guide that will help you negotiate your way through the classification once you've described a soil morphologically in the field, and also once you've obtained sufficient lab data. So this is, I give credit to this idea from my old major advisor at UC Riverside, Lanny Lund. And what it does is we have here, for example, the most common epipetons that you might encounter in the upper left-hand corner: mollic, umbric, and ochric. The rarer ones are like anthropic, melanic, and plagan are right here. And then finally, the organic ones are histic and pholistic. Now, if you can't see this on your screen very well, what I've done is I've posted this checklist on your Moodle site separately. So if you want to pause the video and go and print out or have visible on the side this classification checklist, that might be a handy thing to do. Now, what we do when we approach epipetons, either in the field or using lab data, is we're going to try to put the mollic epipeton on trial. We're going to try to rule that one out at the very beginning. And so another part of this checklist is up here where these stars are. And what you would want to do is, either from field data or lab data, is in this little rectangle right here, you would want to write down the depth to which a mollic epipeton's organic carbon criteria were met. So for example, you would write down the depth to which your organic carbon met that criteria, or you would want to write down the depth to which the color requirements for a mollic were met. Remember, there's a dry color requirement and a moist color requirement. Dry mollicks have to be the value has to be 5 or less, and moist, the value and chroma has to be 3 or less. So you'd write the depth to which those criteria were met. And then also the base saturation. If you were working from lab data and had some base saturation information, you would write the depth to which it was met over here. Remember that the difference between a mollic and an umbric is that a mollic has greater than 50% base saturation and an umbric has less than 50% base saturation. So that might help you sort those guys out too. Now, for mollic epipetons, if you look at the criteria in your 12th edition of the Keys to Soil Taxonomy, this information would not be found on pages 7 and 8, but rather on page 9 of the Keys. This is kind of a schematic that helps you figure out whether your mollic is thick enough or not. And this chart here and down here are helping you sort of decode criteria 6 on page 9 of the Keys. You may want to pause the video right now to turn to that page. Okay, read one of the clauses, such as 6a. So it's saying here that the minimum thickness of a mollic is 25 centimeters if, and for example, if the texture of the epipeton is loamy fine sand or coarser throughout, down here in this little corner of the soil textural triangle, or if there are no underlying diagnostic horizons and the organic carbon content of the underlying material decreases irregular with increasing depth. So what I've tried to do in this chart is kind of depict or dissect or portray differently these criteria 6A, B, C, and D that are on page 9 of your Keys to Soil Taxonomy. It becomes really complicated when you go down to criteria 6C, and in that case, the minimum mollic thickness kind of has a sliding scale here, depending on the depth to different other features. So, for example, uh, um, the mollic thickness is depicted here along this axis. It has to be 18 centimeters thick or 25 centimeters thick, depending on depths to these different features. So try to take a little bit of time and study this. See if you can make heads or tails of that criteria 6C on page 9. We will have a lot of practice for this, and hopefully these little diagrams are kind of job helpers that will help you figure this out. Don't get too discouraged at this point, but I'm trying to build you some tools here to help you figure things out. Okay. Now let's move on to a consideration of the subsurface diagnostic horizons. And again, these start to be described on page 11 in the keys. In this checklist, the most common subsurface diagnostic horizons that we'll see are arranged in the left-hand column. So argillic, candic, and natric, and cambic are pretty common. Calcic, petrocalcic, and salic might be found in arid zones. And also gypsic and petrogypsic might be found in arid settings where they're not intensively leached out. Durpans are silica cemented. There's a durpan right there. The agric is very rare and will not be discussed very much further. Fragipans are brittle horizons that are found more commonly in northern states where glaciation has occurred. And then placic, albic, ornstein, and spodec are associated with spodosols. The glossic horizon we'll talk about a little bit later. Sombric is found in cool mountainous areas in the tropics, and we probably won't spend a lot of time on that. And then oxic horizons are very commonly associated with oxisols, and they're intensively leached. They have few weatherable minerals in them, more often with quartz and aluminum and iron oxides. So that's a quick overview of the subsurface diagnostic horizons. So let's go ahead and start talking about some of these diagnostic horizons. The first grouping that I'll talk about are what are called horizons of alteration. For example, a cambic horizon. This is the taxonomic term that has specific criteria, and this is the morphological designation that we would probably see on a profile description. So cambic is described on pages 12 and 13 of the 12th edition of Keys to Soil Taxonomy, if you want to turn to pages 12 and 13. One of the first things that you'll notice is that it has a texture of very fine sand, loamy very fine sand, or finer. We don't want to have textures that are too coarse on cambics. It also doesn't meet any requirements of other diagnostic horizons. It doesn't have it isn't an AP horizon, and it doesn't have a brittle manner of failure. What cambics usually do have is some kind of color change, some kind of development of soil structure, an absence of rock structure, and or removal of carbonates or gypsum. It's been modified in some minimal way. Now, I want to talk a little bit about rock structure because this confuses people sometimes. This is not synonymous with soil structure. Soil structure would be something like subangular, blocky, prismatic, granular, whatnot. However, rock structure, if you can kind of imagine looking at a soil that was developed in a schist with its foliations, or perhaps slate or limestone with bedding planes, if you could see the bedding planes or foliations inherited from the rock material from which the soil was developed, that would be considered rock structure, not soil structure. So what they're saying here is that this soil has to be altered enough that you're not really looking at the rock structure. Some of that has been obliterated. Okay? An oxic horizon is also, it's usually indicated by a BO designation, and an oxic horizon is described on page 15, And an oxic horizon has thickness requirements, and one of the main things that it has to have is less than 10% weatherable minerals. So this is something that's been super leached, super weathered out. Weatherable minerals are things like feldspars and hornblende and things like that. And these horizons would probably be made up mostly of quartz and iron and aluminum oxides. This kind of horizon also has to have a clay increase, similar to an argillic horizon, except it's very intensively weathered. It would also have a low cation exchange capacity. Okay, let's go on to horizons of alluviation. I think I skipped a slide. There we go. Horizons of alluviation would include argillic, natric, and candic horizons that I want to group together here, and they would usually have a BT or maybe even a BTN designation morphologically. BTN would be for the natric. BT would probably be more for the candic and argillic. And what I'd like you to do is I'd like you to look at the descriptions in the Keys to Soil Taxonomy and try to write down some notes about thickness, clay increase, structure, etc. All these criteria for all three of these different kinds of horizons. Try to pick out the main differences between them. So go ahead and pause the video, look at the requirements for these subsurface horizons and fill out this table, taking about 5 or 10 minutes to glean some of their differences. Okay, go ahead and pause the video now. Okay, the main point for argillic, natric, and candic is that they all have a clay accumulation of some kind. The candic horizons are found in highly weathered settings, but not as highly weathered as oxic horizons. So think of Ka for kaolinite. They're dominated by kaolinitic clays. The natric horizons you probably saw had a special criteria for exchangeable sodium percentage or sodium adsorption ratio. So these are the ones that we would find in arid environments that have some kind of accumulation of sodium. So think of Na for sodium right here for natric. There's some more horizons of alluviation, including calcic, petrocalcic, gypsic, petrogypsic, salic, and durapans. These are all horizons of accumulation to differing degrees, and usually a calcic would be indicated by BK, petrocalcic, we'd put the M on there to indicate cementation, BY for gypsic, BYM for petrogypsic, BZ for salic, and then BQM for durapan. Durapan is cemented by silica. Not strictly speaking quartz, but you can use the Q to remind yourself that silica is involved. These horizons have thickness requirements and clauses that separate them one from another. For example, a calcic horizon is not cemented, but a petrocalcic horizon is cemented. And you should, in your notes, write some notes that help you separate all of these one from the other. Here are some more horizons of alluviation. We have spodic horizons, and we need to talk separately about spodic properties because that's pretty gnarly chemical stuff. But spodic horizons morphologically are often indicated by a BH, BAS, or BHS horizon. H is alluvial humus, S is alluvial sesquioxides. Ortstein is something that would often be associated with spodic horizons and would probably be indicated morphologically as a BSM. So there's a little cemented thin layer that is probably similar chemically, but it's really hard compared to these other things. A glossic horizon is associated with the degradation of an argillic, candic, or natric horizon, where clay and iron oxides have been leached out. So you would look, when you're looking for a glossic horizon, you'd probably be looking for some EBT combination. And the root word gloss means tongue, as used in glossary. And this relates to where there are regions of E horizon tonguing down into an underlying horizon. Finally, for horizons of alluviation, we also have fragipans, which would be indicated by BX morphologically. And fragipans have a brittle consistence, and they're oftentimes found in association with formerly glaciated landscapes. Sambric horizons, as I mentioned briefly before, are found in cool tropical mountainous plateaus. They're accumulations of humus, and they won't be discussed here any further. They're pretty rare for our purposes. Now, a horizon of eluviation, contrast that with illuviation. Illuvial means it's moved, something is accumulated, where eluvial, with an E, means that something has been removed. And our horizon of eluviation is the albic horizon. Again, there are some specific albic soil properties that we need to talk about separately, but albic, alba, is light colored, and it would probably be labeled as an E horizon, light colored and leached. Okay, now going back to our checklist, we've covered kind of a checklist approach for epipetons, for the subsurface diagnostic horizons, and then there's another section of this checklist that deals with things called other diagnostic features, and we have to pay attention to these too. Here's a sampling of other diagnostic features. These are the ones that are most common for us, and please emphasize these in your studies. These other diagnostic soil characteristics start on page 17 in your Keys to Soil Taxonomy. So you may want to turn to page 17 and pause the video while you find that. So for example, andic soil properties are going to turn out to be really important for andisols, that order. Another one would be secondary carbonates. Those are important for figuring out whether you have calcic horizons and so forth. There are things called lithic discontinuities, aquic conditions. Slick sides are oftentimes seen in vertisols. And then in the western United States, where we have a lot of soils, and in wildland soils in particular, where we have a lot of mountainous derived soils, we may run into lithic and paralithic contacts. So please emphasize these features in your study. Okay, we're near the end. Thank you for sticking with me this long. I'd just like to provide you with a summary slide. Epipetons, subsurface diagnostic horizons, and the other diagnostic features are the three main groupings that help us sort out soils taxonomically into one of the 12 soil orders. So clumping these three things, figuring out what's the epipeton, which all soils have, what are the subsurface diagnostic horizons, which some soils don't have subsurface diagnostic horizons, or they may have one or more, so this one is a little bit more variable. And then other diagnostic features, like andic soil properties, are really important to line out, and then you start going to key out things into orders and then suborders and so forth. We use the checklist as a tool to keep organized when you're classifying a soil profile. I think the checklist is really important in keeping things straight and organized so you don't get too confused by the keys. They are not easy to go through, but if you have a firm idea of what the epipetons are, etc., you'll have more success in classifying the soils. The last thing that I'd like to make sure that you know how to do is we're going to start building what are called formative elements in our list of terminology. And in Soil 260 or in your other introductory soils class, we had you memorize what are called formative elements. And these are little syllabi or building blocks that we'll use to build our names of soils. So the last syllable in a name, in a taxon, is going to, in most taxons, is going to indicate what the order is. For example, if we had a lithic tori orthent, ent, you would know that that's in entisols. An EPT means an inceptisol. This is an alphasol. This is an ultisol, oxisol. OLL is for mollisol. EL is for gelisol. IST is for histosol. AND is for andisols. ERT is for vertisols. ID is for iridosols, and finally OD would be the formative element for spodosols. So now that you've listened to these two videos and you've done your reading assignment in Buell at all and looked over the keys to soil taxonomy, this is the point at which you would want to take the online reading quiz. You only have 30 minutes to take the reading quiz. There's 10 questions, and you have to finish this by Monday night at midnight. So good luck with the reading quiz. It's only worth a little bit of points, but it's a good encourager to get you to study this material. Okay, thank you very much, and we'll talk to you on Tuesday in class.